Okay, hello my people, I hope we're doing well. Now we are going to talk about those dreaded values that are not familiar unit circle ratios. Okay, what do we do with those? Because we know that, if I have cosine x is equal to 1/3, that's going to have two values as well. It's just not going to have unit circle values, so it winds up being just a little bit more difficult. But not inordinately so. So let's go ahead and let's start off with this one. This first one kind of is, probably shouldn't have been the first one that we did, but let's go ahead and do it. Sine x is equal to 4/3. Where is sine x equal to 4/3? The answer is nowhere. Because if we're thinking about this being the unit circle, right, and this point right here is 0, 1, where sine is this is the largest sine value you can get, and that largest value is 1. If we're looking for a horizontal line is up here. It does not intersect the circle. Or if you just think about it in terms of the sine function, right, you have a function that looks like this. Well, that's 1. 4/3 would be up here. It doesn't intersect, right? And if it doesn't intersect, then it represents a ratio that has no solution. It's kind of like, when is the sine ratio going to be 4/3? And the answer is never. And your calculator will confirm this. If we just do, inverse sine of 4/3, it takes us to the error screen. Okay? If you get the error screen like that, one of two things has happened. You have either plugged something in wrong, you've made a keystroke error on your calculator, or you have something that has no solution, right? Just like when you were looking for solutions for quadratic functions, every once in a while you ran across a quadratic function that did not cross the x-axis, right? It was a parabola that was either wholly above or wholly below the x-axis. And when that happened, you had something like, you wound up having x squared is equal to -5. Well, x squared is equal to -5 is basically the quadratic equivalent of sine x is equal to 4/3. It doesn't make sense. There is no solution. Now, when we come down here, there actually will be a solution for this one. For those of you who are not great about estimating certain things like this, root 5 divided by 3 does have an absolute value less than 1. Okay, because for those of you, but it's probably a good idea to be able to sort of memorize a couple of the common square roots to 1, 2, or 3 decimal places. But root 5 is about 2.2. Okay, it's just shy of 2 1/4. And divided by 3, of course, that's going to give me a negative, basically right about -3/4. And remember that when we're dealing with cosine, we're dealing with x displacement, right? So it's basically going to be here. And that means that these 2 points right here correspond to that horizontal displacement, okay? And basically this is going to be an ordered pair that is -0.745 blank, right? And this is going to be -0.745 blank. I really don't care about the blank right now. I care about where these are positioned around the unit circle, right? And so if I were to take that value, okay, up here, let's go ahead and make that convenient for ourselves, and we go ahead and take the inverse cosine of that, we're going to get 2.412 radians. Well, that is going to be that right there. That is 2.412 radians. And the reason I know it's that one and not this one is, first of all, pi is 3.14, so it has to be shy of pi. But I also know that when I do arc cosine, when I do inverse cosine in my calculator, it's using the function. And the function arc cosine only exists in the first and second quadrant. Okay? Now, remember that this angle measurement can be represented as negative 2.412. So this angle right here is a full revolution minus 2.412. So it's actually, if this right here is 2.412, then this angle right here is 2 pi minus 2.412. Okay? And we can easily get that from our calculator. We get 2 pi minus that answer. And it's basically, if I'm looking on 0 to 2 pi, then I would give the answers, x is equal to 2.412 and 3.871. Okay? If I were doing it on negative infinity to infinity, I would, just like if it were pi over 6, I would put 2.412 plus 2 pi n and 3.871 plus 2 pi n, and those would be my answers. It's a little bit frustrating when so often you're dealing with radian measurements only in terms of pi, to all of a sudden have something that is just a decimal answer. But it doesn't make it any less a radian. It just makes it a radian measurement that's not familiar and comfortable for us, okay? But a radian measurement nonetheless. Alrighty, let's go ahead and look at the tangent. Tangent x is equal to negative 1/5. Okay, well remember that tangent is neither the horizontal nor the vertical on the unit circle. But I know that tangent of x is negative up here in the second quadrant, and tangent of x is negative down here in the fourth quadrant. Furthermore, I know, let me see if I can, let me tilt this real quick so I can at least get it close to. Where the reference angle is pi over 4, I know that here tangent is going to have a negative 1, right? So here, tangent of negative pi over 4 is equal to negative 1. And here, tangent of 3 pi over 4 is negative 1. But I also know that here, okay, tangent of x is equal to 0, because that's where sine is equal to 0. And here, tangent x is equal to 0 as well. So my 1/5 has to be somewhere in here where the sine ratio, like the vertical measurement of the ordered pair, is 1/5 of the horizontal. Okay, and so you're probably, somewhere around here, maybe? I don't know. I mean, I'm just estimating. But we can go ahead and look at that. But it's important to actually recognize this fact because this angle measurement is exactly pi units away from that angle measurement. And that's important when we start trying to sort of list it out. Okay. And we get negative 0.197. Now the reason why we got negative, remember, because the range for arctan is negative pi over 2 to pi over 2. So it's not going to give us the positive measurement right here. If it gives us the negative measurement of 0.197, okay, then all you have to do to get the positive, all you have to do to get the positive is just add 2 pi, right? That's 6.086. Okay, well, to get the one that's halfway around, you simply have to, either add pi to the negative one or then subtract pi from the 6.0, and you get 2.944. Okay, now, and here's the thing, it's pretty low, and it's pretty close to 3.14 because for the vertical displacement to be 1, 1/5 of the horizontal displacement, it's got to be pretty low in that quadrant right there. Now, if we were asked for it on 0 to 2 pi, I would simply give this one and this one. Careful not to give the negative one, right? 2.944 and 6.086. Now, if I was asked for it on the implied domain, notice that I'm no longer putting negative infinity to infinity. I'm putting implied domain because tangent doesn't exist at its asymptotes, which of course occur periodically. And I don't want to deal with trying to express that or explain how to right now. But we understand that 2.944 would be the first angle measurement, and then it would be every period before and after that. Okay, last one of these. Let's go ahead and do cosecant of root 6. Now, some of you are thinking, I'm not going to do that. I'm going to go ahead and flip that bad boy to 1 over root 6. And that is fantastic, and that is exactly what you're supposed to do. Let's go ahead and find out what that is in terms of an estimate. 1 over root 6, and you get 0.4, roughly, okay? So basically what you have here, now remember, sine is measured in the vertical. And so if that's 1/2, then 0.4 is probably right about there. And you want to find the two places on the unit circle that correspond to that y measurement. And that's here and here. Now at 1/2, you are going to be at pi over 6. So this is going to be an angle measurement over here, this first one. The reference angle on both of them are going to be less than pi over 6. But notice, because the reference angle, because this being theta and this being theta prime, the two angles, this and this one, are going to be supplementary. So the moment that I find my arcsine of that answer, okay, I know that my other one is going to be its supplement. Because if this is theta and this is theta prime, then this angle and theta prime are going to add up to 180, or add up to pi radians. And so if I'm asking for it on 0 to 2 pi, then I simply give this first and second quadrant angle measurements of 0.421 and 2.721. And if I'm asked for it on the implied domain, meaning no restrictions except for the restrictions placed on it by the form of the function itself, then I basically have x is equal to 0.421 plus 2 pi n, and x is equal to 2.721 plus 2 pi n, basically every period before and after that. Now, this has all been kind of leading up to these graphical problems that we discussed. A couple of them in the class period. Okay. So let's say that we have this function, and I'm asked to identify the transformations and graph it. Well, that should be easy enough, right? And since cosine is even, I can just flip that difference around and eliminate that transformation. I know that I'm going to move over pi. I know that I'm going to vertically stretch by 1.5 or 3/2, and then I'm going to move up 3/2 units. Now that means that that basically what was a function that oscillated between -1 and 1, when you stretch it, oscillates between 1.5 and -1.5, and then when everything moves up 1.5, it oscillates between 0 and 3. So I need to scale my y so that I don't have a problem there. Let's go ahead and scale it like that. The only thing that that's going to do is it's going to give us just a smidge of a problem when it comes to identifying the axis of oscillation, but whatever. Because it's going to be in the middle of one of these boxes. But let's go ahead and do pi, 2 pi, and 3 pi. Now let's go ahead and do the parent. And we wind up with sorry, it's sometimes I can talk while I'm doing this, and sometimes I feel like I need to concentrate because my mind is not at its peak right now. Okay, there we go. Now, this, of course, is our parent. You do need to be able to draw these quickly, okay? And so we're going to take all these points, and we're going to move them to the right pi. Then we're going to vertically stretch them by 3/2, and then move them up 3/2. And this point moved over, stretched, and then moved up, okay? This point right here, let's do it this point right here. This moves over pi units, so 1, 2, 3 boxes. And then it stretches by 3/2. Well, 0 doesn't stretch. And then it moves up 3/2 units, so to here. So right in the middle of that box. So I probably could have done a better job of scaling this, but let's just continue. Let's take this point. Let's move it over pi units. Let's stretch it by 3/2, and then let's move it up 3/2, and boom, we get that point right there. Now, I also know that the period hasn't changed, so that goes there, that goes there, and this goes here. This point right here, still periodic, goes here and here. And then, of course, we have the corresponding point. Let's do this one right here. We'll move it over pi units, stretch it, and then move it out 3/2. And we have something like this, okay? And I'm not going to do the intervening points. My point right here is not for the graph. Otherwise, I would put a couple more points and make it a little bit more accurate. But for our purposes, that's accurate enough. Now, this, of course, is the new axis of oscillation, which is always my y is equal to d line. Okay, this is y is equal to 3/2. Now, you know how to do that much, but now we can actually look at, okay, I'm looking for the maximums. Well, the maximums are here, 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 and here. Let's see whether we can actually work it out analytically such that we can confirm that. And all you have to do is just ask the function an output-based question, which in this case is, Mr. Function, when do you have outputs of 3? Okay, well, when do you have outputs of 3? Now we simply need to solve for x, and just like any other solving of equations, we need to undo what's being done to the variable in the opposite order in which it was done, right? And so we subtract 3/2 from both sides, and then we divide both sides by 3/2, and then at this point we're asked, when is cosine equal to 1? Well, you should know when cosine is equal to 1. Cosine is equal to 1 at when the angle measurement is 0. Okay? Well, the angle measurement here happens to not just be the variable, but an expression. So whatever the angle measurement expression is, we set it equal to the answer to that question. Cosine is 1 when the angle measurement is 0. And every coterminal after that, before and after. And then all we have to do is simply add pi to both sides, and I should get my maximums at pi, 3 pi, 5 pi, 7 pi, and on and on and on and on and on. And that is exactly where we see them. Okay, well, let's look for solutions. And in this case, the solutions are actually the minimums, right? And in order to look for the solutions, I simply ask my function another question. I say, Mr. Function, when are you 0? And again, I go through the process of solving the equation by subtracting both sides by 3/2, and then dividing both sides by 3/2. And now I'm asking, when is cosine equal to -1? Well, cosine is equal to -1 when the angle measurement expression is pi. But not just pi, every coterminal after that. And so x is equal to 2 pi plus 2 pi n. And that's telling me that I should have my solutions at 2 pi, 4 pi, 6 pi, 8 pi, but also 0, -2 pi, and -4 pi. And I see that that is exactly where I have them. So my analytic work has lined up rather nicely with the graph that I've been given. And that, makes me happy. Yay! Alrighty, I'm going to go ahead and bring this video to a close. We will explore some more of these types of problems, and these types of problems will be on your tests. Will be on your weekly quiz. I'm going to do maybe one, maybe two more videos on these to make sure that you kind of get the cadence of how to work them, but also understand conceptually the logic of why it is that we're doing what we're doing. Okay. If you have any questions, as always, shoot me a message. Bye.